Okay, so this is section 8.1. It's actually the only section that we're going to talk about this particular during this year in chapter 8. There are other important sections in here, just not something that we're going to cover for the AP test. Section 8.1 is called the arc length. And if it sounds familiar, you may have dealt with that a little bit in pre-calculus when you're talking about the length around the outside of the arc of a circle. It's a very similar concept, but we're actually going to show how it's kind of developed. So we're going to be able to find the arc length of a curve in the Cartesian coordinate plane. Basically, that's your standard XY plane. The reason I say that is because we're also going to be able to find arc length given parametric equations as well as polar equations, which is going to come up later in the second semester. So what is meant by the length of a curve? So if you can imagine taking a string and laying the string exactly on top of a curve, then removing the string, stretching it out, and then measuring it with like a ruler or something. Because the hard part to do would be to actually measure the curve using a ruler. You'd have to basically be able to bend the ruler. And there might be those out there, but in this case, I think it's easier to understand. Again, if we take some kind of a string and put it on top of a curve, and then you stretch the string out, and then you can measure that straight length with a ruler. That's what's meant by the length of a curve, how long that curve would be if it was stretched out. So obviously, a string is not going to always be available to us, and curves can be much larger than we would have even if we had the string. So we're going to use some calculus concepts to figure this out instead. So the first thing we're going to do, we're just going to sketch a curve. Okay, it's going to just be, it could be any given curve. It doesn't really have to look like anything in particular. But there's my curve. Along the curve, we're going to label a bunch of points. So we have an initial point. We'll call that P sub 0. We have an end point. We'll call that P sub n. Which, because we don't know exactly how many points there are. Obviously, there's an infinite number of them, but we do have a last point. That would be P sub n. Then we're going to have a bunch of points in between. So we're going to call this one, like right here, P1. And then we're going to call this one up here P2. And then we're going to call this one right here P sub I minus 1. We're going to call the one that's over here P sub I. So those are just any two general points. Obviously, the I minus 1 meaning it's the point right before P sub I. So what you have to do is you have to kind of imagine the fact that these are infinitely close together. So what we've done is we've zoomed way in on some piece of a curve. And that's kind of hard to imagine, but that's what you kind of have to imagine, that we've zoomed way in on some piece of a curve. The idea or the concept is this. I know that I can measure the distances between these points. I can measure the distance between P sub 0 and P sub 1. That was not very straight. Something more like that. But what you'll see is it doesn't exactly match the curve. I could also measure the distance between P sub 1 and P sub 2. Then I can measure the distance between P sub 2 and P sub I minus 1, and so on. What we are doing in general is we're measuring the distance between every two consecutive points. And then if we were to take all of those distances and add them up, we would have a decent approximation for the length of the curve, but it's not going to be exact. As a matter of fact, let me go ahead and fill this last one in here that we didn't do. And then you would have a bunch of other points leading all the way up to P sub n. But what if we actually let those points be so close together that you can't tell the difference between the two? So the 2 points are going to get infinitely close together. Okay, and this is where you kind of just have to use your imagination a little bit and actually kind of see this. We're going to let all these p-values start to get infinitely close together, and then we're going to measure the distance between them. Well, if you do that, if you zoom in far enough, the distance between any 2 points, like over here, would just be that part of the line, or that part of the curve. then the distance between the next 2 points would be that part of the curve, and then that part of the curve, and then that part of the curve. And what you would see is, if you let these points become infinitely close together, you are going to get the exact measurements on the curve. So we know how to find the distance between 2 points, and that's ultimately what we're going to do. So we can use line segments to estimate the length of the curve because we know how to find the distance. Again, if we take smaller and smaller intervals on the curve, and then we let the number of line segments that we've created approach infinity, we're going to get the exact length of the curve. And that's exactly what we're going to do. All right, so let's look at the next page. This is going to be a 1 video lesson, by the way. So we're going to take the length of the curve, which we're calling L. It's going to be the limit as n approaches infinity, because we want an infinite number of them. And we're going to take the sum of all of the line segments from p sub I minus 1 to p sub I. So this right here, whoops, didn't mean to erase, that represents a line segment between 2 consecutive points. The absolute value is there because if we count it backwards, it's fine, but that would give you negative values, and we need the absolute value there because of the fact that these are all going to be distances. They're going to be positive. And then we're going to add them all up. Well, if you remember correctly, the limit of a sum is an integral. So we are going to integrate all of the line segments. Well, the real question would be, how do I get those line segments? This is actually one of the few times I am not going to prove and or show where the formula comes from. This is actually something I will show when we get to Calculus 3, for those of you going on to Calculus 3. And if you don't ever see it, then you can always come back for a proof if you want it. But this is one of the few things I am not going to do. But what this does come from is the distance formula. Hopefully you can see that this piece right here, this square root, is the square root of 1 plus a derivative squared. 1 and a derivative squared are 2 things squared. So if you were to square both sides and set that equal to something, you would basically have a Pythagorean theorem. You'd have an a squared equals b squared plus c squared, or something like that. Solve for one of them, and you would get this one. So if f prime is continuous on a closed interval, then the length of the curve between the 2 endpoints is going to be given by the integral from a to b, 2 endpoints, of the square root of 1 plus f prime of x squared dx. Okay, there's different ways that you can write this, which we're going to show below. And it's also important to understand that this, again, can be extended into parametric and polar curves, which again will be, it says later this semester. It's actually most likely going to be second semester in this case. So you can also write the same exact thing. Instead of writing f prime of x, we can write dy over dx, which is this one right here. Same exact formula. You might want to take a look at the next one, though. The next one says that you can write it as dx over dy. Notice that you have a dy on the outside here. That's just because what we've done is we've basically solved the equation in terms of y as opposed to in terms of x. So we've made it a function in terms of x as opposed to y. So when you take the derivative, the x part is the dependent variable, where the dy part is going to be the independent variable. It could happen that way. Just know that you would have the dy on the end if you had to solve in terms of x. We'll show that in the next page. So we are going to have to find these derivatives by hand in some cases, and a lot of times I think on your homework and your web assign you will have to try and give the exact answer by hand. But in reality, most of the time you're going to be able to use the calculator to evaluate the actual arc length of something. So we're going to do it both ways, at least for one problem, and then the second problem we're just going to use the calculator. All right, so our first example here, we're actually going to find the length of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. And we are gonna look at this on this graph on the calculator. But I want to make sure you understand, first of all, you don't need to know what a semi-cubical parabola is in order to do the problem. It's just kind of neat to know that that's what we're going to be doing. You're going to have to solve this for either y or for x. Doesn't really make any difference in this case, but I do want you to see what it looks like. So let's go ahead and bring this up on the calculator. So the first thing I'm going to do is I'm going to solve this for y. So if I solve it for y, we're going to take the square root on both sides, which means if I take the square root on both sides, we're really going to get the plus or minus square root of x cubed. Don't forget the minus part because it is part of the actual graph. So let me bring the calculator back up here. So if we graph this, there's no way to put plus or minus, at least not that I'm aware of, in the TI-83 or 84 calculator. So we're just going to have to do it separately. So we'll do the square root of x cubed. And then we're going to do the negative square root of x cubed. And let's go ahead and take a look at what this looks like. I'll do a zoom 6, standard graph. That's kind of an interesting thing. It looks like it comes to like a cusp there right at the origin. So if we sketch this, looks like it's going to look something like this and something like that. Basically, it's a mirror image over the x-axis. And because the y was squared, hopefully you figured out already this was not a function, which is why I've not been saying let's call it a function. So we're just going to solve it for y in this case. So we want to figure out the arc length between the points 1, 1, which would be approximately right there, and 4, 8, which may be someplace up here. We want to find that arc length right there. So the length between those two dots. So we really didn't need the negative part in this case, but it was still good to be able to see it. All right, according to our formula, the arc length is the integral from a to b of the square root of 1 plus, now because of the fact that this is a y and not a function, I'm not going to write f prime of x because it's not really a function here. I'm going to write this as dy over dx squared dx. So I am doing this in terms of x, which means that my bounds need to be in terms of x. Well, here's a, here's b. Those are the x values. We're going to go from 1 to 4. So let's go ahead and figure this out. We're going to have an integral from 1 to 4, square root of 1 plus. We need the derivative. So we're going to have to find y prime in this case. So y prime, again, I'm only dealing with the positive part, is going to be the derivative of the square root of x cubed, which remember is x to the 3/2 power. So the derivative of that is going to be 3/2 x to the 1/2 power. So I'm going to have 3/2 x to the 1/2, oops, forgot my 1/2. 3/2 x to the 1/2 power squared. Don't forget the square. Okay, so this is actually one that we can do by hand. And then we'll use the calculator and show it's all the same. So I'm going to take an integral from 1 to 4, square root of 1 plus squaring, that's going to give us 9/4 x dx. So now we have to go back to some techniques that we've learned in the past. We're going to have to do a u substitution here for our composite function. 1 plus 9/4 x is u. So du is just going to be 9/4 dx. Solving for dx, we'll multiply both sides by 4/9. So dx is going to be 4/9 du. I'm also going to go ahead and change the bounds, just because that's the way I prefer to do it. So when I change the bounds, if I plug in 1 for x, it's going to be 1 plus 9/4, which is going to be 13/4. Okay, these are not nice bounds, but it's what we have to deal with. If I plug in 4 for x, I'm going to get 1 plus 9, which is 10. Whoops. And then we're going to have the square root of u times 4/9 du. Okay, I can take the 4/9 out to the front. It's a constant. Integral from 13/4 to 10 of u to the 1/2 power du. And then I can do the antiderivative, which is going to be 4/9. U to the 1/2 is going to become u to the 3/2. Dividing by 3/2 is multiplying by 2/3. And then I'm going to evaluate that from 13/4 to 10. This is not going to be a pretty value. So it looks like we're going to get 8/9 of 10 to the 3/2 power minus 13/4 to the 3/2 power. Whatever the heck that is. We'll figure that out because we'll plug it into a calculator in a little bit. All right. Now I'm going to show that this could have been done another way. It could have been done by, instead of solving for y, solving for x. So down here, I'm going to solve this thing for x, which means that x would have been the cube root of y squared, which is the same thing as y to the 2/3 power. So then x prime would have been, what is that, 2/3 y to the negative 1/3 power. So another way to solve this one would have been to find that the arc length, now this is all in terms of y, so it's going to go from 1 to 8 because those are the y values of the point, of the same exact formula basically. So it's square root of 1 plus the derivative, which we just found to be 2/3 y to the negative 1/3 squared dy. This one I am not going to attempt to do by hand. As a matter of fact, this one will be very difficult to do by hand. So what I'm going to do is I'm going to leave that one to you guys to plug into your calculator. One thing I want to make sure that you understand is just because the variable says y here does not mean you can't still use x. So just use an x when you put it in a calculator and it will still work. So now what we're going to do is we're actually going to go back and we are going to plug in this into our calculator and show that it's going to be the same value as this. And I will leave the other one to you to show it's exactly the same thing. Okay, so let's go ahead and do an integral in the calculator. Clear this out. So the integral is going to be math 9, 1 to 4 of the square root 1 plus 9/4 x, 1 plus, let's do a fraction that looks like a fraction, 9/4 x dx. Okay, that should give us what our answer is here. So it says that the answer is supposed to be, whoops, keep forgetting to do that, 7.6337. 7.6337. Now let's actually go ahead and plug this answer that we got for our exact answer, which is this one right here, into the calculator and see if that works out. So 8/9, 8/9 of 10 raised to the 3/2 minus 13/4 raised to the 3/2. Assuming that I plugged all this stuff in correctly, it should give us the same value. Let's see if we did this right. I did not do it right. What did I do wrong? I see what I did wrong. Hopefully you caught this before I did, because I can't seem to multiply basic numbers. That should have been 8/27 there. So let's go ahead and fix that on the calculator and see if it works. So Don't know if you know you can do this, but you can just hit enter on your 89, on your 84 calculators, and then go back and fix the missing number instead of retyping the whole thing in. It's just a lot easier. So we're going to type 27 down there, and now let's see if it works. There we go, 7.6337. So we've got exactly the same answer. And again, I'm going to leave this one for you guys to plug into the calculator. It should give you exactly the same thing. Okay, one more example, and then we're done. And this one, we're just going to strictly do calculator. Find the length of the arc of the parabola y squared equals x. Again, this one's already in terms of x equals. There's no reason to change it. We have the points, so we're going to do everything in terms of y. So the length of the arc is going to be from 0 to 1. Fortunately, you really couldn't mess that one up since the point goes from 0, 0 to 1, 1. Of the square root 1 plus, so now I have to find x prime, which is going to be 2y, and then x prime squared is what goes in the parentheses, and this will be dy. So let's go ahead and plug it in the calculator, and we'll see what we get. Math 9, 0 to 1, integral of the square root of 1 plus, I'm just going to write this as 4x squared. Remember, it can be x, does not have to be the fact that there's a y in there. You don't have to type in a y. It's just a variable. And we get the arc length 1.4789. 1.4789 approximately. And that's it. That's really all there is to arc length. So it's just making sure that you can solve the equation if necessary for a variable, taking the derivative, plugging it into the equation. The hardest part is going to be doing some of these by hand, which is going to be like the ones above, but it's going to be something where you where it can be done if it wants the exact value. Otherwise, you can use a calculator to check your answers. All right, that's it. One video.